Let us now study about the energy conservation when we have a loop here and then we move the rod from one place to another place, from right to left. Okay, so in this picture you can see the magnetic field is represented by a vector. It's pointed into the board, so you can see the tail feathers like this way. Okay, like this here. Now you can see the rod is moved from right to left. Okay, so in this case you see, okay, what will be the energy conservation? You have to see that. First, for that you must see when you move this rod from right to left, okay, there is a opposing force here. Okay, the opposing force is given by this FB. That's the opposing force. Okay, so this FB, that opposing force, okay, that's the magnetic force here. Okay, or the force on a conductor in a magnetic field. Okay, that F is equal to, we have to see that it is IL, okay, cross B vector. Okay, this is a current element and this is a magnetic field. So this comes from the formula, that is F is equal to BIL. Okay, we have learnt it earlier. Okay, that formula is used here. Now let us see this how it comes here. A vector dot B, A vector cross B vector is equal to AB sin theta. That formula is used here. A vector cross B vector is equal to AB sin theta. Okay, so now see here in this thing, okay, let's substitute in C. So we'll get here ILB sin theta. Okay, so sin of what's the angle here now? Okay, see here this AB is a current element here. Okay, that is IL. Okay, so AB is that IL. Okay, and this is a magnetic field. See the angle between them. Okay, this angle is 90 degrees. You can see this angle will be 90 degrees. So sin 90. Okay, so sin 90 is this one. That is 1. Okay, so we can write theta also. Okay, so actually it will be sin theta. I'll write one step now. Okay, ILB sin 90. Okay, because theta is equal to 90 degrees. We saw how it comes. Okay, when we substitute in C, sin 90's value is 1. So it's ILB. Okay, so this is the magnetic force cell. Okay, now let us see what will happen now. Okay, when you push the rod from right to left. Okay, so this is the magnetic field. I'm just drawing, or we just see in the same picture itself. Okay, so when you push this way, okay, this is a magnetic force now. Okay, magnetic force is opposing it. It's like this way, from left to right. Okay, we have to give a force from right to left. Okay, that force that we are giving is called as a F opposite. Okay, the force that we are giving. Okay, so better I'll draw it in a separate picture itself, not here. I'll draw a separate picture. So this is the magnetic field here. Okay, this is a magnetic field, and then this coil here. Okay, this rod here AB. Okay, so this was FP, the magnetic force, and the force that we are giving is F opposite. Okay, this will be more clear. Okay, okay, when you see two separate pictures here. Now let us see this thing. In this case, if you see, this two forces will be equal and opposite if the rod is moving with a constant velocity. Okay, so velocity is constant. So in this case, the magnitude of the opposing force, okay, will be equal to the magnitude of the magnetic force. That will be equal to this one, that is ILB. Okay, we don't put plus or minus signs. Why? Because we just take the magnitude. Okay, now what happens is this mechanical work is done in this case. Okay, so in this case here, mechanical work is done. Okay, and then we know that the rate of doing work is called as power. Okay, the rate of doing work is power. Okay, so why mechanical work is done? We are giving the energy. Okay, so we are doing mechanical work here. Okay, so let's see the power here. So power is equal to F into V, F dot V. Okay, this is a formula here. Okay, so in this case, the power will be equal to the opposing force, that force that we are giving. Okay, F opposite into the velocity here. Okay, a dot product here. Okay, so let us see this dot product. A vector dot B vector is equal to AB cos theta. Okay, now you see here that will be F opposite and V and then cos theta. Okay, so now see that velocity and this F opposite will be in the same direction. Okay, velocity is in this direction. Okay, from right to left, and the F opposite also is in the same direction. So in this case, theta is equal to 0 degrees. Okay, so we substitute cos 0. Okay, so F opposite into V into cos 0. Cos 0 value is 1. So we get here power is equal to F opposite into V. Okay, let us substitute the value of F opposite and see here. I'll drop that side. So let's substitute and see here in this formula F opposite. Okay, so power we got here, that is equal to F opposite into V. So substitute the value of F opposite. Okay, that will be ILB into V. Okay. Now next what you must do, substitute the value of I also. Okay, substitute value of I. Okay, so I we learnt earlier. Okay, that I came to be I is equal to BLV by R. Okay, so this was the equation. Substitute and see here instead of this I. Okay, so what happens is we get here BLV by R, okay, into LBV. Okay, so this LBV here. Okay, so BLV, LBV both the same. So multiply and see that. So we get here B square L square V square by R. Okay, that's the power here. Okay, so this is one equation you see. So let's take it as equation number 1. Okay, now let us see this thing. Okay, when the current is flowing in this thing, okay, so current is produced here. We saw that using Fleming's right hand rule, the current was going like this way. Okay, this direction here. Now what happens is when the current is flowing, okay, so Joule heating takes place. Okay, so let us see this now. I'll rub this side and we'll see the part. So let us see this now. Okay, I'll write down for you. So let us see this now. Okay, so when induced current flows, Joule's heating takes place. The rate at which thermal energy is dissipated or power dissipated, we will see. Okay, so when current flows inside the wire, there will be heating. Okay, so that they say Joule's heating happens there, and the rate at which thermal energy is dissipated. Okay, power means what? Energy by time. That is the rate at which energy is dissipated. Okay, let's see the power here. So using this Joule's law of heating, we get power is equal to I square into R. R is the resistance here. Okay, now what happens? You substitute the value of I here. Okay, right here, substitute the value of small I. Okay, so substitute the value of small I, that is BLV. So what you get is BLV by R, the whole square into R. Okay, so that will be B square L square V square by R square into R. So R and the square will cancel. So we get here B square L square V square by R. So this is the power here. Okay, so let's write this as equation number 2. Okay, so equation 1 is equal to equation 2. So equation 1 is equal to equation 2. Equation 2. Spelling mistake again. Equation 2. Okay, so what do we understand from this? Okay, so we are giving the mechanical energy. Okay, the mechanical energy changes into electrical energy. Okay, the induced electrical energy. Then the energy cannot flow anywhere now, so it is changing into heat energy. Okay, so energy is changed from one form into another form. Okay, it is not destroyed here, it is not created also. Okay, that proves the law of conservation of energy. Okay, so in this case what happens here? So first we are giving mechanical energy. Okay, how mechanical energy is? We are pushing the rod from right to left. Okay, so that is the mechanical energy. That energy changes into what? It changes into next one, that is electrical energy. Okay, it changes into induced electrical energy. Okay, and that electrical energy changes into what? It changes into heat energy. Okay, so one form of energy is changed to another form of energy. So that is why we can say the law of conservation of energy is proved. Law of conservation of energy is proved. Okay, from this example. Okay, so thank you for watching.